welcome to Engineer's Mindset. So in this video, we are going to be looking at how to draw the sharpness and bending moment diagram for a simply supported beam with a uniformly varying load. Now we have a question on the board and we are asked to draw the sharpness and bending moment diagram for this beam. So you have the beam carrying a 10 kilonewtons load and a uniformly varying load whose intensity is 20 kilonewtons per meter. Our first task is to draw, of course, our free body diagram, right? So let's start with the free body diagram, FBD. Okay, so you pull down your beam. Okay, now remember this is a pin support, and for the pin support we have two reactions. One is vertical at the point of occurrence, the other is horizontal, all at point A. So let's call this RAY vertical reaction, RAX horizontal reaction. Now at point B we have a 10 kilonewtons downward force. So we have a 10 kilonewtons downward force. Distance from A to B is actually 2 meters. This is point B. Now we have here, this is point C. From B to C is actually 1 meters. Now at point D we have a roller support. Obviously we are going to have one reaction which is normal to the surface, called this RDY for the roller support. Now we need to first of all convert the uniformly varying load to a point load. The reason why we are doing this is to be able to find the unknown reactions RAY and RDY in this diagram, so we can be able to carry out our analysis. So the first task is to convert this UVL, which is uniformly varying load, into a point load. And to convert a uniformly varying load to a point load, simply take the area of the shape. Now the area of this shape is triangular. So we are going to be simply taking the area of a triangle. And what's the area of a triangle? It means that the point load becomes what? Half times the base times the height. Where the height becomes the total what? Load carried, it is 20 kilonewtons per meter. The base becomes the total length of the UVL, which is 3 meters. So that means this point load is going to be equal to 1 all over 2. The base there is 3 meters. The height is maximum load, which is 20. So you simply have 3 times 20, that's 60, multiplies 1 over 2. So the point load is actually what? 30 kilonewtons. Now when you do this point load will now be placed at a distance 1 all over 3 from the base of the UVL, or 2 all over 3 of the length from the tip of the UVL. Remember, this point load now, 30 kilonewtons, will now be placed either at the base of the UVL at 1 all over 3 of the length of the UVL from the base, or 2 all over 3 of the length of the UVL from the tip. This is the tip of the UVL, this is the base of the UVL. The length of the UVL itself is what? 3. So this point load will be placed at either 2 all over 3 of this length, 3, and 2 over 3 of the length is going to be what? 2 meters from the tip, or 1 all over 3 of the length, and the length is 3 from the base, and 1 over 3 times 3 will simply give us 1 meters from the base. Whichever way you go about it, any one you choose, you're going to have the same result. So this simply means that from the tip, 2 over 3 of the length of the UVL is 3 meters. So from this tip, measure 2 all over 3 out of these 3 meters, and 2 over 3 out of that 3 meters give us 2 meters. So it simply means from the tip, which is from point C, you measure out what? 2 meters. 2 meters will be somewhere around here. So this means from point C to where this point is acting is 2 meters. That means the remaining length becomes what? 1 meter. So remember, from the base is going to be what? 1 meter, which is what we obtained here. So if you have measured out 2 meters, it simply means from the base it becomes what? 1/3 of the length, which is this case is also what? 1 meters. The point load now, remember, is 30 kilonewtons. Okay. So this is now our free body diagram. Our task now is to use this free body diagram to determine our support reactions. And in the first video I explained that you can use 2 ways to obtain our support reactions. You can use the moment to moment equilibrium equation method to obtain the reactions, or you can use the combination of the first equilibrium equation and the moment equilibrium equation to obtain that reaction. So in this video I'm simply going to use the moment to moment equilibrium equation method because it seems very easy to be used, right? Okay, now what is this method all about? It simply states take moment at each of the points of the unknown. I have unknown reaction here, which is RAY and RAS. I also have unknown reaction RDY at point D. So I will simply take moment at each of these points. So first, let's take moment at point A. So we simply take moment at A. So summation of moment at point A is going to be taken as 0. We consider clockwise moment as positive, anti-clockwise moment as negative. Now, if you take moment at point A, moment simply means force times the perpendicular distance which the force makes about the point of moment. If I'm taking moment at point A, these forces RAX and RAY have no distance about point A. So it means their distance is what? 0. Therefore, the moment of these two forces about point A automatically becomes 0. So we are going to now take the moment of every other force on the system about point A. So you see that by taking moment about point A, you have nullified the effect of these two forces about that point, right? So we simply take the moment of this 10 kN force about point A. This force is acting downwards, which means its moment will turn in this direction to take moment at point A. And what direction is this? We said clockwise should be taken as positive, and this is a clockwise direction. That means the moment of this 10 kN force about point A becomes positive. Total distance it takes this force to get to point A is simply what? 2 meters. Therefore, the moment becomes 10 times 2. You have this. Next, you take the moment of the 30 kilonewtons force about point A. Once again, this force is pointing downwards. That means this force will turn about in this direction to take moment at point A. And this direction, once again, is a positive direction, which we assume clockwise direction. Total distance it takes this force to get to point A becomes, remember, from here to this point, 2 meters plus 1, that's 3 plus 2, that's 5. So you simply have plus 30 multiplied by 5. Finally, you have the RDY pointing upwards. That means this force will turn about in this direction to take moment at point A. And that direction is anti-clockwise. And anti-clockwise, we say, should be what? Negative. Total distance it takes this RDY force to get to point A becomes the total length of the beam, which is simply what? 3 plus 1, 4 plus 2, 6. So you simply have minus, because it's anti-clockwise, RDY multiplied by 6, and this is equal to 0. Okay, so let's evaluate now. 10 times 2 gives us 20, plus 30 times 5 gives us 150, minus 6 RDY, this is equal to 0. 20 plus 150 is 170, so you simply have 170 minus 6 RDY equals 0. So let's simply send 6 RDY over there. You have 170 equals 6 RDY. So with this now you can find the value of RDY. That becomes 170 divided by 6. So let's simply obtain 170 divided by 6. That gives us RDY to be equal to. So RDY gives us approximately 28.3 kilonewtons approximately. So the reaction at point D is simply 28.3 kilonewtons. So you simply repeat this same procedure now from point A. So we are going to now be taking moment at point D. So choose each of the unknown locations or unknown reactions and take your moment about that point. That is the second approach. I taught this in the first video. So do well to check out the playlist, apply techniques. You're going to find the first video to properly understand this, right? So again, we take moment now at point D, one of the unknown. Even though we found the value now, simply take moment at point D. The reason why is that if you decide to take moment, let's say at point B, now that you know this unknown force, already the value to be this 28.3, you're going to be taking moment of that force also at point B, and that might lead to multiple equations, and that will trouble you a little bit. So simply take moment at point B, so that the moment of this force about that point becomes 0. You have only one unknown now to contend with, and you simply find your RAY. It's as simple as that. So we simply take moment at point D now. So we take moment at D. Summation of moment at D is equal to 0. Again, we consider clockwise positive, anti-clockwise to be negative, right? So we simply take moment of the entire force about point D. Mind you, when a force lies on the same plane as the plane of moment, the moment of that force about that point becomes 0. So RAX is purely horizontal. It is still on the same plane as the point of moment, the plane of moment. Therefore, the moment of RAX about that point becomes 0. Now we have RAY. Remember, moment must always be force times perpendicular distance, but RAS is purely horizontal, lying on the same plane as the plane of moment. So the moment of RAX about point D becomes completely 0. Now we take moment of RAY about point D. RAY is pointing upwards, so which means it will turn in this direction to take moment at point D. And this direction is what? Clockwise. This direction is clockwise. You say left clockwise is positive. This direction is clockwise. So the moment of RAY about point D becomes positive. And the total distance becomes total distance of the beam to get to point D, which is 2 plus 1, 3 plus 2, 5 plus 1, 6. So you simply have RAY multiplied by 6. Again, you have this 10 kilonewtons force acting downwards. The moment of this force about point D, this force is acting downwards. That means it will turn about in this direction to take moment at point D. And this direction is what? Anti-clockwise. You say let anti-clockwise moment be negative. So the moment of this force about point D becomes negative. Total distance it takes this force to get to point D becomes 1 plus 2 plus 1, which is actually 4. Okay, so you simply have minus 10 times 4. And finally, we take the moment of 30 kilonewtons force about point D. This force is also pointing downwards, which means it will turn in this direction to take moment at point D, anti-clockwise. And total distance becomes simply 1 to get to point D, right? So you simply have minus 30 times 1. The whole of this is equal to 0. So you observe now that the moment of RDY, even though it is known, but since we're taking moment at the point where RDY is, it means there's no distance between that force and that point. So the moment becomes the force times 0. And that simply gives us 0. So the moment of RDY about that point automatically becomes 0. Okay, so if you evaluate this now, you are going to have 6RAY minus, this is 10 times 4 here is 40, minus 30 times 1 here is 30, equals 0. So 40 minus 30 simply gives us minus 70. Minus 40 minus 30 here simply gives us minus 70. So this simply implies that 6RAY minus 70 is actually equal to 0. Let's say negative 70 over there. You have RAY is going to be equal to 70, right? Divided by 6, because negative 70 cross and equal to sign becomes positive. Then divide both sides by the coefficient of RAY. You simply have 70 divided by 6. So this will simply give us the value of RAY, which is the reaction at point A. So let's find 70 divided by 6. So that gives us approximately 11.7. You have 11.7 kilonewtons. So the reaction at point A is approximately 11.7. Okay, so now that we've found the reaction, the next thing we simply do is head straight into our shear force and bending moment analysis. Okay, so to carry out, first we start with our shear force analysis. Okay, so for the shear force analysis and the bending moment analysis, we are simply going to be using the original beam because we want our UVL to still be in this form, right? We don't want the free body diagram. We are going to be working with our original beam because we want that UVL for a particular reason to set up what is called the shear force equation. That will help us to determine the if you're asked to find the point of maximum bending moment and the point of contraflexion, it is with that shear force equation that you are going to do that. So that's why we need the UVL to be on the beam, right? Now we'll start with our shear force analysis. Shear force simply means the stepwise summation of the entire force acting on a beam from beginning of the beam at each point of the beam to the end of the beam, considering vertically upward force to be positive and vertically downward force to be negative. So you start from beginning and you add up the entire force to the end of the beam. So you take upward forces as positive, downward forces as negative. So you start from point A. The force that exists at point A is 11.7 kilonewtons, and this force is pointing upwards. Since it's upwards, it means the force is positive. So therefore, shear force at A equals 11.7 kilonewton, and it is positive because it is pointing upwards. Now, this is the next thing you do. This same force moves from point A to point B initially. So you simply say shear force B prime, which means initially this same force 11.7 moves from point A to point B. But on getting to point B, you observe that there is a 10 kilonewtons force acting downwards there. So therefore, you label that as shear force B prime prime, which means finally at point B, this 11.7 kilonewtons force experiences a downward force of 10 kilonewtons downwards now, so it becomes what? Negative, minus 10. And this is going to give us simply 1.7 kilonewtons. So this same shear force moves now from point B down to point C. So you simply label it shear force at point C. Now, the reason why you will say shear force C prime is simply because at point C, there is actually no force. So you actually use that prime to indicate initial if there is a force there. Then you use prime prime to now say after or finally, after encountering this force at this point, right? But at point C, there is no existing force. Rather, there is a force between point C and point D. That force is not at point C. It is between point C and point D, right? So this means, for this reason, you simply say shear force C. C remains the same shear force as what you obtained initially. So this 1.7 kilonewtons force simply moves down to where? Point C. You have 1.7 kilonewtons. That becomes shear force at point C. Now, between C and D, there is a strange type of load that is there. And that load is simply called a uniformly varying load. For this purpose, you now do what is called sectioning. You simply take a section from point A, from beginning of the beam. You take a section at about any point on the UVL, right? You take a section from point A, you label the distance as x from point A about the point, any point on the UVL just before it gets to the end of the UVL. You call that distance x. Now let's do this and see. Now you simply take a section, just take a section at about any point here, just before it gets to the end of the UVL. So you simply label from here to that point, you call that section in x. You call the length from point A to that point x. Take a section xx at a distance x from point A to any point along the uniformly varying load. The reason why we are doing this is simply because the shear force diagram and the bending moment diagram will change structure or shape when it gets to this strange type of loading. For that reason, that will require us to find what is called the point of maximum bending moment and the point of contraflexion. And to find the point of maximum bending moment, you need the shear force equation. Then to find the point of contraflexion, you need the bending moment equation. And that is why we are doing this, right? So with this now, you can be able to get the shear force equation and also get the bending moment equation. So if you're taking distance from point A to the point of the UVL just before it gets to the end, you call that distance x. That simply means that distance of the UVL about the point of section, the UVL about the point of section is from point C about just the point of section, which is somewhere around here. This distance is now going to be equal to what? Remember, if from point A to this point is x, you now want from point C to the point of section. Now, the idea is this. You count, what we need is just from point C out of x. So from point C simply means we are now neglecting 2 and 1 out of this x. Remember, from point C, we just need from point C to the point of section. So we are taking off from point C out of this x. And remember, we have 2 plus 1 inside this x. So if we are now cutting off here and say we just need from point C to this point, it means we've taken off from here to this point out of x, because from point A to the point of section is simply x. So if we're taking off here, from here, if we're just considering from point C to this point, it means we're taking off everything here out of x. And everything here includes what? 1 and 2. So 1 plus 2 is simply 3. So we are simply taking away 3 from x. Therefore, the length from point C to the point of section becomes what? X minus 3. That becomes the length from point C to the point of section. Very simple. So with this, you can now form the shear force equation. What is the shear force equation? Alright, so the next thing now is you make your shear force statement down. What we've done so far, you put it down in a statement. Now, consider section XX. Consider section XX at a distance x from A along CD, which is where you took your section, right? Along C to D, you took section somewhere around CD. Okay, now you now find shear force CD. This is going to be equal to, so remember, this 1.7 kilonewtons force moves initially, so you put it down 1.7 kilonewtons. Now, since you know that the UVL will always is acting downwards, as can be seen, so which means its force is going to be negative because it's acting downward. But now the UVL now have a new length. We are considering the length of the UVL about the section, which is x minus 3. And remember, we have to convert this UVL towards a point load first. So since we're talking about shear force, you have to convert it to point load. And what is now the point load of UVL? Remember, point load is simply half times base times height, where the height is a maximum load carried, which is 20 kilonewtons per meter. And the base is the length of the UVL about the point of section. The length of the UVL about the point of section is now x minus 3. Therefore, it means that our point load becomes what? Half base x minus 3 times height, which is what? 20. This becomes now our force for the UVL. So 20 times 1/2 is obviously 10. So you have 10 into x minus 2. So you have 1.7 minus 10 into x minus 3. Now you realize that the idea was actually to find the shear force at point D, right? The essence of doing this is just for us to be able to obtain our shear force equation, which we've obtained here. And at this point, if you equate this equation to 0, you're going to find the point of maximum bending moment. When you find the value of x, the value of x obtained when you equate this equation to 0 becomes the point of maximum bending moment. But the idea is to find the shear force at point D. So now we simply consider at D. At D, what happens? X now has a value. Remember that X runs from point A along CD. So it starts from the beginning of the beam, then somewhere around C to D. But we want to find the moment, the shear force at point D. And at point D, that means X simply extends from point A down to point D. So at point D, X becomes the entire length of the beam. And the entire length of the beam is what? 2 plus 1 plus 3, which is 6. So at point D, x is now equal to 6. X now has a value, right? So at point D, x equals 6. So you simply plug that into this equation. You're now going to have that shear force at D initially. So since there's a force at point D, we simply call that shear force prime, which means shear force initially at point D, because at point D, we have a force existing there. So this is going to be equal to 1.7 minus 10 into x is 6 minus 3. Okay, so this is going to be equal to, so I will simply evaluate everything all together just to save time. So 6 minus 3 is 3. 3 times 10 is 30. 1.7 times minus 30, please. 1.7 minus 30 will simply give us negative 28.3 kilonewtons. So this is now the initial shear force at point D. But finally at point D, there's a force 28.3 kilonewtons pointing upwards. Because it's pointing upwards, it becomes positive, right? So that simply brings us to shear force D prime prime, which means finally at point D, this force negative 28.3 encounters a positive force plus 28.3, and the value gives us what? 0. Again, at the end of every shear force analysis, you must always obtain your result as 0. So we are done with the shear force analysis, and our end result simply means 0. This shows that the beam is under static equilibrium. All right, the next thing to do is the bending moment analysis. So we start the bending moment analysis. Let's segregate here. Okay. Bending moment analysis. Now, from equilibrium law, the moment of force about any point is 0, right? So the moment of this force, RAY, about point A automatically is 0. So moment at point A equals 0. Now, moving down to point B, the moment of this 10 kilonewtons force at point B is also 0. But now at point B, we have this force 11.7 kilonewtons force has a distance about point B. So we can find the moment of this force about point B. Now, when doing bending moment analysis, always consider the moment of vertically upward force to be positive, whereas the moment of vertically downward force to be negative. Okay, so we are now at point B. Moment of force at point B becomes the moment of this force 11.7. Total distance it takes this force to get to point B is 2 meters. Multiply that by 2. So we're simply going to have this to be, let's obtain 11.7 multiplied by 2. That gives us 23.4 kilonewtons meter. So we'll have 23.4 kilonewtons meter. Okay. Next, we find the moment at point C. Okay. Moment of force at point C. Once again, we simply take the moment of now 11.7 kilonewtons force and the moment of this 10 kilonewtons force about point C. So for the 11.7 kilonewtons force, total distance it takes to get to point C becomes 2 plus 1, which is 3. So you simply have 11.7 multiplied by 3. Since it's pointing upwards, each moment is positive about that point. Now we have 10 kilonewtons force pointing downwards, therefore it will exert a negative moment at point C. Total distance it takes this force to get to point C is 1 meters. So you simply have minus 10 into 1. Therefore, moment at point C is going to, let's evaluate everything. 11.7 multiplied by 3 minus 10 times 1. That simply gives us 25.1 kilonewtons meter. 25.1 kilonewtons meter. Again, just like we did previously, on encroaching into between C and D, there is a strange type of loading which is called the uniformly varying load. For that reason, we consider our section. We've already done the sectioning there, but always ensure to state down your section or write down your section statement, right? So consider section XX at X from A along CD. So you simply find the moment of force along CD. Now, this is what happens. This helps us to now form the bending moment equation. It is the value of X from this equation that tells us the point of contraflexion. When you equate the bending moment equation to 0, the value of X obtained is called the point of contraflexion. Now, we are simply saying from point A to somewhere along CD is X. And we have established that the length of the UVL about the point of section from point C to the point of section is X minus 3. We have established this. Now, remember, moment is force times distance. So if we're not taking moment about the point of section, it simply means that the moment of this RAY force is going to be this force times total distance it takes this force to get to the point of section. For distance from point A to the point of section is X meters. So the moment of the 11.7 kilonewtons force about the point of section becomes what? 11.7 multiplied by X. It's as simple as that. 11.7 multiplied by X, because the total distance it takes this force now to get to the point of section is simply X. That aside, we want to now take the moment of the 10 kilonewtons force also about the point of section. Remember, we are now considering now from point B to the point of section. Since we are considering from point B, it simply means we are taking off anything behind point B out of X. Remember, from here runs to point B. So if we want to take from point B, it means we are taking off everything from here to this point out of X. And from here to this point is simply what? 2 meters. So it means that the distance of this 10 kilonewtons force about the point of section becomes what? X minus these 2 meters. Distance of this 10 kilonewtons force about the point of section becomes X minus 2 meters, because we're starting from point B. So we're neglecting the whole of this distance. We're taking it off from X. So total distance it takes point B to get to the point of section becomes from here to the point of section is simply what? X minus 2. This becomes the distance of the 10 kilonewtons force about the point of section. So the moment, since that force is pointing downwards, its moment is negative. So you have minus 10 into X minus 2. It's as simple as this. That's how you form a moment equation, right? And finally, we are now in the territory of the UVL along CD. First, we need to convert the UVL to a point load. We have done that already. This is our point load. 10 into X minus 3. That's our point load. Remember, half base times height is the load. The point load is simply half base times height, where half base there simply means the length about the point of section, which is x minus 3, where height there is a maximum load carried by the UVL, which is 20. 20 times half is 10, so you simply have it to be, since it's acting downward, it becomes negative. So you have minus 10 into x minus 3. But this is just a point load and not a moment. So remember what I said earlier, that after taking your after converting to point your UVL to a point load, the next thing you do is you place it at 2 all over 3 from the tip, 2 all over 3 of the length from the tip, or 1 all over 3 of the length from the base. So if you place from 2/3 of the, now let's say this is our UVL, okay, about the point of section, which is x minus 3. Now from 2/3, which is now this point C, which is the tip, 2/3 becomes somewhere. This is our point of section, not forgetting XX. Now 2/3 becomes from here somewhere to somewhere around here. This is our 2/3 of the length. So from here to this point becomes 2 all over 3 of the length x minus 3. That means the moment of this force now, this our point load about the point of section becomes what? The remaining length from here to this place. The remaining length from here to this place will not be what? Remember, it's going to be the 1/3 of the original length from the base. So 2/3 from the tip, 1/3 from the base. So after converting this to point load, you place it at 2/3 from the tip. This is 2 over 3 of the original length x minus 3. It ends here. And we want to take a moment about the point of section. The remaining distance becomes 1/3 of the original length. And 1/3 of the original length becomes 1 over 3 times. Original length is x minus 3 about the point of section. That becomes our moment. So this is now our force. Therefore, our moment becomes multiply this by 1 all over 3 of x minus 3. This becomes our moment. It's as simple as this. So this equation is called the bending moment equation. If you equate this equation to 0, the value of x you obtain here is called the point of contraflexion. That is that point where the bending moment diagram changes sign from positive to negative or from negative to positive. It's called the point of contraflexion. Okay, so we are done with our moment equation. The next thing to do now is now take our moment at point D. At D, remember, x is going to now be total length of the beam, which is 6. So you simply plug in the value of x as 6 into this equation. So it means that moment at D is going to now be equal to 11.7 in place of x. X is 6 minus 10 into x is 6 minus 2 minus 10 into x is 6 minus 3 times 1 all over 3 into x is 6 minus 3. So let's evaluate everything and see. Moment at D equals, let's find 11.7 times 6. So 11.7 times 6 is approximately 70 minus 6 minus 2 here is 4. 4 times 10 is 40. Okay. Minus, I have 6 minus 3. That is 3. 3 times 10 is 30. 30 times 1 over 3 is 10. 10 times 6 minus 3 gives us 30. 6 minus 3, of course, is 3. 3 times 10 gives us 30. So you can see already from here, this is equal to 70. Negative 40 minus 30 is minus 70. And this is equal to 0. So just like I said, once you plug in the value of x as said in that equation, you have your result to be what? Simply 0, which means our analysis is very much complete. Now we are done with our shear force and bending moment analysis. The next thing we simply do is to plot the diagrams. So to plot the diagram, you trace all the points down. Trace all the points down. You can use a freehand sketch, it's highly permitted, or you can use a graph sheet. You trace all the points down. You trace all the points down. So you start with the shear force and pick out the highest values and the lowest values. Okay, from the shear force analysis, my lowest value is 0. Apart from 0, I have 1.7, and then my highest value seems to be 11.7. So approximately I have just two values, 11.7, 1.7, and 0, right? Okay, so just three values. So 11.7 seems to be the highest. So you trace the origin. This is our origin. 0, 0. 11.7 can be kept here. 11.7 kilonewtons. Then you have 1.7. You can keep that here. 1.7 kilonewtons. Okay, so you trace out the points. Trace out the points. Trace out the points. Trace out the points. Okay, let's now plot our shear force diagram. Shear force at A is 11.7. This is line A, not forgetting. 11.7 is here. This is where it connects. So you asterisk shear force at A. Now that shear force moves from point A down to point B. So you still have 11.7 initially at point B. So shear force at B initially still remains 11.7. Finally at point B, you have 1.7 kilonewtons. So finally at point B, it steps down to 1.7. This is 1.7. This is line B. Finally, it steps down here. So you asterisk. Now that same force moves from point B down to point C. So shear force at C remains 1.7 kilonewtons. So from B, it moves down to point C. C remains 1.7 kilonewtons. On getting to point C, it encounters a strange load, which took the shear force to point D initially to be negative 28.3. Okay, so we have negative 28.3. So let's indicate that here. Negative 28.3 should be somewhere here. 28.3 should be down. Negative should be down, right? Okay, below the 0 mark. So trace it out. Okay, so shear force at D initially is negative 28.3. So this is line D. So initially you have it here, negative 28.3. And finally shear force at D. Finally shear force at D is simply 0. So finally shear force at D is simply 0. These are 0 mark, right? So you asterisk here and you have this. So let's now connect the points. The shear force diagram for a point load is simply a straight line connecting each of the points. So I have a point load here, RAY. So from the origin, you draw a straight line to connect to this asterisk line, right? Or asterisk point. So a straight line to connect the points. You have this. Same thing, that same force move from point A to point B initially, still a point load. So you connect these 2 points. Again, still a point load acts down to connect to this, so you connect with this. This same load moves from point B to point C, you connect. But now you have a UVL. The shear force diagram for a uniformly varying load is simply a slant line. The shear force diagram for a UVL is simply a slant line to connect each of the points. So you draw a slant line connecting these points to these points, and you have this. And finally, shear force at point D becomes 0. So finally, at point D, a point load once again. So you simply connect with a straight line, and that's it. So you asterisk here, you draw shaded lines like this. So this becomes our shear force diagram. So you observe the change of sign. This is positive. This is positive. Let me use red. Okay, so this is positive and this is negative. You observe the change of sign from positive to negative. That is the point of what? The point of maximum bending moment. The point where shear force changes sign from positive to negative is called the point of maximum bending moment. And that is why we form this equation. The value of x at this point will tell us the point of maximum bending moment. You can also determine it using this shear force diagram. Okay. Now, we are done with the shear force diagram. Next, we'll draw the bending moment diagram. So just like we did in the shear force diagram, let's pick out the highest number from the lowest, right? So moment at B, 23.4. We have 25, seem to be the highest for now. 25, any other value, 0. So 25 is the highest, followed by 23.4, and then 0. So we can simply call here our baseline. That's our origin, 0, 0. Okay, that's our origin, 0. All right. So moments at C is 25.1. That's the highest. So let's keep here as 25.1. 0.1 kilonewtons meter. Moment at B is 23.4, so followed by 23.4. Can call here 23.4 kilonewtons meter. Okay, with other moments, I think the remaining is 0. Okay, so let's trace out these points. Trace out these points. Trace out these points. Now, moment at A is 0. This is line A. This is 0. You simply what? Asterisk. Moment at B is simply 23.4. This is line B. This is 23.4. This is where they meet. You simply asterisk. Moment at C is 25.1. This is line C. This is 25.1. You simply asterisk. This is 25.1. This is line C. You asterisk. Moment at D gives us 0. This is line D. This is 0. You simply asterisk. Now, the moment diagram for a point load is simply a slant line connecting each of the points. So I have point loads up to point C. So simply a slant line, connect from here to this with a slant line. Okay. Connect also to this with a slant line. Now, between C and D, we have a uniformly varying load, right? The bending moment diagram for a uniformly varying load is simply a hug curve, like a curve that is hugging, right? So you simply draw a curve and you have something like this between C and D. So it's basically a curve. Okay. So that becomes our bending moment diagram. So you can easily asterisk, you can shade. You can easily shade. Okay, so you can see the point of maximum bending moment from the diagram. Of course, you can see that point. Let's just shade. So this is our bending moment diagram, and this is our shear force diagram. Okay, so that's the diagram for the question. So just in case you're asked to find the point of maximum bending moment, you can evaluate that with this diagram, or you can simply come here, equate this to 0, find the value of x. The value of x given to you becomes the point of maximum bending moment. But that is not for this question. I will do a separate video altogether for that particular question. Okay, so here ends the video. Please do well to like the video, share to your friends, comment nicely, and of course, if you're new to the channel, do well to tap the subscribe button and turn on your bell notification so you don't miss out on our subsequent videos when it drops. I will see you in the next video. Cheers.